We are continuing our study the linear algebra 2, and today we are looking at the schedule section 4, which is titled Cayley-Hamilton Theorem. But before then, you can recall from our previous study how to find the hidden value problems of the system of linear equations, whereby you will have your A is equals to lambda n, and you know what we call the characteristic equations. So we are still continuing in that point. But before we continue, we want to look at some theorems. Which are related to Cayley-Hamilton theorem. And the first theorem is if lambda 1, lambda 2 to lambda n are characteristic roots, this thing or not of the matrix A of order n, and if g of A is any polynomial functions of A, then we have the characteristic root of g of A, which are given as g of lambda 1, g of lambda 2, up to g of lambda n. That is the first theorem. And when we go further, we establish, we prove the theorem. Then the second theorem, if the characteristic root of A, the characteristic roots of A are lambda 1, lambda 2 up to lambda n, and those of A raised to the power of B, where your B is any integer, lambda 1 raised to the power of B, lambda 2 raised to the power of B, up to lambda n raised to the power of B, provided the inverse of A exists. That is, before you can have that, the matrix A must have an inverse. Then the third theorem, which is Cayley-Hamilton theorem, says if A is a square matrix of order n, then A satisfies its characteristic equations. The determinant of A minus lambda I is equal to 0. You can still remember our I, which is identity matrix, and the lambda, they are the constants, they are the characteristic roots. That is, the determinant of A minus lambda I must equal to A raised to the power n plus alpha 1, A raised to the power n minus 1, plus alpha 2, A raised to the power n minus 2, plus c alpha n of I equals to 0, where your alpha I are given as 1, 2 up to n. They are the constants. They are the constants, that is the coefficients. Example, to establish the Cayley-Hamilton theorem that says that the characteristic polynomial is equal to 0. Given the system of equation 2x1 plus x2 equals to lambda x1, then x1 plus 2x2 equals to lambda x2. This is a question, this is a system of linear equations. So we want to prove the Cayley-Hamilton theorems on this. That is that the characteristic polynomial, the characteristic equations of this problem is equal to 0. From here, we can get our matrix A, which are the coefficients of the variable x1 and x2. And we have our A to be 2, 1, 1, 2. That is 2 by 2 matrix. The characteristic equations is given as the determinant of A minus lambda I. What is I? Is the identity matrix, and the lambda is a constant. where your A is the matrix from the equations given to you. And A is 2, 1, 1, 2, 2 by 2 matrix, minus lambda, the identity. The identity for 2 by 2 matrix is 1, 0, then 0, 1 is equal to 0. So when you minus it, you have 2 minus lambda, then 1, 1, 2 minus lambda. So when you find the determinant of this, you will have 2 minus lambda multiplied by 2 minus lambda minus 1. So when you do the multiplication, you do the arithmetic operation there, you will have your lambda squared minus 4 lambda plus 3 equals 0. The theorem says, remember the Cayley-Allington theorem says, that A satisfies its characteristic equation. A satisfies its characteristic equation. So you set your lambda to be equal to A. Anywhere you see lambda, you substitute with A. That is, you are going to have that A minus lambda I. So you are having a lambda squared. So instead of lambda squared, now you have A squared minus 4 lambda. Instead of putting lambda, you put your A plus 3, which is identity matrix. So you will have it as A squared minus 4A plus 3I. That is, the determinant of A minus I minus lambda I is given as, you know, you have replaced the lambda now to be A. So instead of you writing A now, you put the matrix 2 by 2 matrix, which is 2, 1, then 1, 2 squared. So minus 4 multiplied by A, and your A is 2 by 2 matrix, which is 2, 1, and 1, 2, plus 3I, that is 3 multiplied by the identity, 1, 0, 0, 1. So when you square the 2 by 2 matrix 2 and 1, you will have 4, you will have 5, 4, 4, 5. Then the next one, you will have 4 multiplied by 8, which is 8, 4, 2, 8, plus 3 multiplied by the identity, you will have 3, 0, 0, 3. So when you find the addition of this matrix, you will have it as 0, 0, that is equal to 0. So that has proved that the Cayley-Allington theorem. Cayley-Allington theorem allow for a representation of I powers of matrix. Suppose phi of A is equal to 0 is expressed in polynomial equations of the form B, form of equation 2. You have phi of A to be equal to A raised to power n plus, that is, if you have the representation in higher power, so it's going to be in form of equation 2, which is A raised to power n plus alpha 1 A raised to power n minus 1 plus alpha 2 A raised to power n minus 2, and so on. They multiply by c, the addition of alpha n I equals to 0. Having computed A squared, A raised to power 3 up to A raised to power n, then we substitute into that equation, so we have the equation 3. Then multiply 2 by A, and substituting equation 1 for A raised to power n to have, after the simplification, you will have your A raised to power n plus 1 to be equals to your equation 4. This means that any positive integer power of n is expressible as a linear combination of 1, a raised to power 2, a raised to power 3, and so on, up to a raised to power n minus 1. In a similar vein, if the inverse of A is not singular, if the inverse of A is not singular, multiplications of equation 2 by inverse will yield inverse of A to be equal to minus 1 over an, that is, it will yield your equation 5. To yield your equation 5. Then multiply the equation 5 by the inverse of A and substituting from 5 for A inverse, you will have your A inverse, that is A raised to power minus 2. By continuations in this process, all negative power may be expressed as linear combinations of A squared, A raised to power 3, and so on. By continuations of this process, all the negative power may be expressed in this form. So far so good. We were able to prove the Cayley-Hamilton theorem. That is, when you are given a system of equations, you will establish that the characteristic equation is equal to 0 by replacing your identity matrix by the matrix you have in the problems given to you. Then you prove that you establish that they are equal to 0. So this is an exercise for you. Given the system of equation 3x x1 plus x2 equals to lambda x1, 2x1 plus 2x2 equals to lambda x2, x1 plus x2 equals to lambda x1. Then 2x1 minus 2x2 equals to lambda x2. Okay, we have two questions here. We have two questions. We have the first one, then the second one is 2 by 2, then the second one is 3 by 3. So show that the phi of A is equal to 0, where A is a square matrix of each of the system of equations. So you have the first two equations, they are the problem. They are the first problem. Then the second three equations, they are the second problem. So you solve it to show that the phi of A is equal to 0.